Hello, everyone. Tapir seems to be ubiquitous this year on Scala. There is one on the slide, one on the T-shirt. At least there was one yesterday in the lobby. Some mascots, even the food truck was full of Tapir. So this is good. This means that there is a chance that things we'll be talking about in the next 30 minutes will be interesting and relevant for some of you. So, as you see, this Tapir is riding a turbojet engine, which probably makes him the fastest Tapir, at least in Warsaw. The question is, why should we Scala developers care? And what it actually means. So let's set the ground by citing the Scala survey results from 2023, where 87% of Scala developers declare that they use Scala predominantly for backend and web development. So I think it's not a secret that Scala is used as to power web servers. And it is also understandable given that we have such two amazing ecosystems of libraries like type level, Cat's Effect, and Zio to write concurrent and resource-safe code. So in our company, we are no different. We use Scala to power our web servers. We use Cat's Effect for that. Side note, we actually use Cat's Effects also for some more esoteric use cases, single-threaded on-caller thread, and using async computations. It's quite nice. Perhaps we'll talk about it one day. But coming back to web servers, the question is what constitutes the web server? It's not only writing a couple of REST endpoints and plugging in business logic. There is a lot of stuff going around. So you have to maintain documentation. You have to keep it up to date. You probably want to expose some clients in different languages. And this all takes time. And these are separate things that have to be maintained. And it would be wonderful if we could use one source of truth to drive all those use cases. So I think that a little bit like mathematicians, Scala developers like to look for abstractions, like we saw a wonderful talk of Nicola a couple of hours ago. And we look for those abstractions and we want to use it for our own benefit. And for that level of abstraction for web servers, Tapir is one of the answers. It takes the approach of describing a web HTTP server as values in Scala. There are other approaches. One notable is Smithy and Smithy 4S, which has its own DSL for that. One final remark before we move on. The tests, we ran a lot of tests and repeated them many times. To benchmark Tapir, use some tools for that, and those tests have been carried out by my colleague Andriy Plokotniuk. Thank you, Andriy. And you may know Andriy from his library JSONiter Scala, which is arguably one of the fastest on the JVM and very safe too. So what is Tapir? A quick recap. Actually, how many of you know what the name comes from? Of Tapir. Okay, some of you know. It stands for Typed API Descriptions. And it's nothing more but describing an endpoint of, let's say, a post or get endpoint with a Scala value. So that's a shortened version of a blueprint of Tapir endpoint. You have wonderful number of 5 type parameters, one for 2 types of inputs, for error output, and for some capabilities. And what it allows us to do later on is to take those Scala values and play with them and interpret them for different servers. For almost every Scala server that is used out in the wild, there is an interpreter in Tapir. You can interpret a client, or you can generate documentation. Open API for REST and async API for WebSockets. So this is quite impressive that you have one source of truth and you can derive all those things. So no surprise that we do use those kinds of libraries like Tapir. Later we will see if there is some price that we have to pay for that. A small, I would say, a pitch slide for Tapir, how it actually works in the code if somebody has not implemented it. We start by defining an endpoint. We add some description, which will be automatically available in the OpenAPI and Swagger documentation, which is really nice. We define that the endpoint is of type GET. And down here, you see the current type of this endpoint. So we do not have any input. We don't have any output. We have units. We don't require any capabilities. So that's why any. And now we can just combine, build in layers those endpoints. So we actually modify the immutable endpoint that we had one line before. We can say that we will have a error output of a specific type. Somewhere there is a implicit codec which will take care automatically of lifting those error responses. We can add a security input, which will be derived from the header of the HTTP request. We can add some inputs. In case of GET requests, there will be two paths inputs. They are all typed. You see this one captured as a string, the other captured as an int. And it is being reflected in the input type. We can add one more. So not everything has to be done in one step. There is a query, and there are some extra lines with those default and description, which once again will land in the documentation automatically. As Scala developers, we don't like tuples that much. We prefer to have it named. And Tapir is nice enough to have some built-in macros which actually convert a n tuple into a n case class. So as long as this, and it gets a compile time warning when this case class the types won't match. So this is how you describe an endpoint, and then you can take this endpoint and do many things with that. Oh, one more. We can also say that the error of the HTTP request will be always a JSON. Oh no, sorry. This is the output. This is the output. Yeah, that's it. Okay, but this was all for REST endpoints, and we are interested in WebSockets. So that's a very short recap of what WebSocket is. It is used primarily if we have some low latency use cases like real-time price updates, financial price updates, or in chat applications, or in gaming where also latency is paramount. So the question is, how do we model this full duplex asynchronous protocol in Java or Scala? So this is the approach, one of the approaches in Java. And it uses good old callbacks to respond to different kinds of events, to a new message, to closing a WebSocket, to an error. This is not bad, but as Scala developers, we're not that not satisfied with callbacks. There have to be ways to make it more Scala way. And luckily, there is a method for that. We can use FS2 or streams to model WebSocket communication. We have heard about FS2 already during this conference. We even had a workshop. So I won't go into too detail about FS2. Let me just highlight that the core of FS2 is of functional streams, that it models incremental changes in reality. Yeah, and we do wrap the effects in, suspend them in effects. And some of those events, some of the values when you create a stream may be available, and some of them may be available in the future. So this is a perfect use case for WebSockets. One more remark with regard to FS2. It's I think this is the library that's visually sits on the top of the complexity of the type level stack. And actually, FS2 predates Cats Effect 3, and Cats Effect 3 has some things directly borrowed from FS2. So it's a great library. Let's use it. And this is a type that will model a WebSocket connection for us. We've got a stream of input WebSocket frames and a stream of output WebSocket frames, and they can. Both streams can be infinite, and it's a function from input stream to an output stream. So how do we describe such an endpoint in Tapir? Well, each WebSocket connection starts as a HTTP connection, so there is some boilerplate. The important part is that there is this WebSocket body. We say that will be JSON transported over the wire, and there are two types, two business level types, WS request and WS response. And it means that, the business logic will be captured in this pipe from WS request to WS response. So this is describing a WebSocket in a high level in Tapir. Okay, let's build some server, and this is a visualization of the server that we were building in our company. Our use case is for real life live updates of financial data. So think about stock exchange, price updates, trades, all sorts of stuff. And the important thing is that the new data, the updates, arrive from some external service at a fixed rate of 100 milliseconds. So this 100 milliseconds is a struct on there. So there are pieces of information, new frames that arrive, new updates every 100 milliseconds, and we are to dispatch those updates to a big number of users. We want to serve, say, a couple of thousand of users. And the goal is that those packets, once the truck arrives at the bottom, the time between unloading those packets and the time arriving at the client is as small as possible, because we want to be real life. And so we use Tapir for that, and we ran some initial benchmarks, and it sort of looked like this. So clearly we have some optimizations to do, and the question is where to start? Yeah? What does it mean that something is slow or fast? So the first question that needs to be answered wherever you do some benchmarks, or you claim that something is too slow, is to define a metric, why something is too slow. And you can have very different metrics with different characteristics for WebSocket. You may be interested in an average throughput when you want to just shovel gigabytes of data to some other place, and you don't care about some local spikes. In our case, we are interested in tail latency, meaning that we want the worst response to be as good as possible. The next thing is how to benchmark, and we will see into it later on. There are a lot of interesting things to pay attention to. And then what to optimize. Primarily, we will optimize Tapir, but not only that. We will also touch on JVM and OS and other stuff. So let's start by defining requirements, and this is one of the most important slides to understand pictures from this presentation. So the requirements are on the left. We want we have a certain latency requirements for our requests. So say we want 90% of the requests be very fast, and we also state the maximum latency, so that no request must take longer than half a second. And on the right here, you've got the latency diagram, which shows the distribution of those latencies. This 90% there means that 90% of the packets of WebSocket frames arrived faster than this point on the blue line. Yeah, and so it's sort of looks at the tail latency. You can look it from the other side. If you take a look at the last number, which has like 99 and 6 nines, it means that if you have 10 or 100 million WebSocket frames, only one will have latency higher than this blue curve. There is a lot of stuff to there is a lot more stuff into it. If there is one thing that I would like you to take away from this presentation is if you ever do any kind of benchmarking, especially web server benchmarking, please take time and watch this presentation. It's an oldie, 9 years from 9 years ago. It's a pretty lengthy one. It's an eye-opening presentation. Okay, you have to speed up a little bit. Let's look at the benchmark setup that we have. It's a quite different benchmark setup from standard HTTP request response REST benchmark. We have two separate machines, client and server, to minimize the influence of the client on the server which is running at its capacity. The clocks are synchronized, and the server actually once the WebSocket connection is established, the server creates a WebSocket packet every 100 milliseconds and puts a timestamp into this WebSocket frame. So these are two connections with timestamps every 100 milliseconds. We have a client. We use Gatling for client to simulate real-world use case. So there is some full scenario described in Gatling when you ramp up the users. Each user consumes a certain number of messages, and also we store the difference between the timestamps into some data structure. And this is how this Gatling report looks like. This is a very nice illustration of what happens actually when you do the benchmark. So you see those spikes up there, which correspond to latency to the cold JVM warm up. Then you have the spike when all the subscriptions have started, and the last spike, which corresponds to closing the subscriptions. And also down here, you see that the rate, which should be constant, is actually fluctuating. And this is one of the explanations why standard Gatling latency is meaningless for us, because it measures time from packet to packet, and clearly the packets should arrive every 100 milliseconds, and you have values which are smaller than that. So this is why we take this another approach of latency measurement. We have so the axis, x-axis is time. We've got server which emits the frames, client which reads the frames, and below here you have the timestamps, the values that are actually stored in the Gatling and in the data structure which is called HDR histogram. I have to speed up a little bit. Let me just show you what happens, because this is the ideal case when everything is working. If the server is running on the edge and there is some delay in emitting another WebSocket frame, we've got a delayed timestamp. And what happens, we've got different scenarios what to do then with this kind of scenario. If we do nothing, then we introduce some lie into our measurements, because we just skip some frames which would introduce some more latency. So are the different approaches to that. You can try to repeat the missed frames, and these are the results that are stored. This is still a bit of a lie, because we repeat with a current timestamp, and the approach that we have is that we repeat those missed frames, but we backdate them to the times that they should have arrived, because this is the real latency. The whole thing is called coordinated omission, coined in by Giltin in this great talk. And this is the example of what difference it makes depending on how you measure. So the blue line is the correct measurement. And you see that if you backstamp those packets, the latency profile is much worse. Okay, let's speed up Tapir. That's Tapir 1.6, which was released 6 months ago. So it's a kind of a time machine, and we take a look at what is the result. The blue line is always our service level expectation. So for 8.3K users, we are okay. And this is the max. It means that if we increase this number, we will no longer meet our expectations. The problem is that this red line down is HTTP4S. So it completely destroys Tapir in this test. How subtle those tests are can be seen in this picture, where you have a saturated version of HTTP4S, the red line, and it works perfectly. So it's almost twice the performance of Tapir. And then when you increase only by tiny bits, less than 0.1% to 15.4K, it completely explodes. And this is due to Java 17, ZGC, and stuff. So this is a very, very delicate case. So what can we improve? And there are many angles, many things that we can improve. Well, we won't be improving business logic. We are primarily interested in improving Tapir, but we will also touch on OS and JVM and server. It's just that those improvements that we are doing took more than half a year, and in the meantime, we did introduce some improvements to OS, JVM, and server. So that's slightly faster Tapir, and these are changes that have been induced outside Tapir code. So JDK22, which was released 3 days ago, all the tests are rerun for JDK22, and that is a list of things that we have changed. For example, disable tracing in Katz effect, some parameters in servers, and stuff. And the results turned out to be great. The blue line is the new Tapir with improvements. We are able to squeeze 11,000 instead of 8, so that's an improvement of 30% without touching Tapir code. But we rerun the HTTP4S for this JDK22, and it still exceeds 40,000 users for this latency profile. So clearly, we are much, much slower still. So we started looking at the culprit. Here is the async-profiler flame graph. A tool which allows you to see to sample your code and see where the CPU cycles are spent. And it's just for comparison, because the time is running. This is the comparison between Tapir and HTTP4S. You clearly see that there is a lot of more garbage collection going on in HTTP4S in Tapir, and also those big spikes on the left. These are Blaze threads. You see that how little time Tapir actually spends on Blaze threads. So where to look? We can zoom in into one of those Blaze threads just to show you how it looks like. There is nothing to search for us here. The orange stuff is the kernel operations, and this is writing to low-level sockets. So let's look at the Katz effect threads. And there is a clear difference between Tapir and HTTP4S. This orange stuff for HTTP4S is actually a thread CPU idling, so the thread is actually not saturated yet. And the one interesting thing that came up is that on the absolute level of CPU cycles, Tapir spends more than 10 times on FS2. So let's upgrade further. We looked at the FS2 code that Tapir has, and this is a small improvement in the code in one of the interpreters. This was extra work that was in Tapir. The results proved that there is a slight improvement. That's the comparison between the old and the new. We are still below our service level expectations. The improvement is not that much. It's only 800, from 11K to 11.8K. So in order to make it, remember, the goal is to hit at least 40K, because this is what HTTP4S is giving. And to improve further, we need to step back a little bit and see what Tapir is doing. So as we mentioned at the beginning, we have this abstraction layer over client and servers. And this is one of the WebSocket abstraction layers in Tapir, meaning that there are some configuration options that are on the Tapir level, and they are completely above the server options, and they have to be implemented by Tapir, and it takes time, as it turns out. So somewhere in Tapir there is a server interpreter. We need to go from high level to an actual HTTP4S server, and this is exactly what it does. It takes a high level pipe of stream. It takes this configuration, and it outputs a low-level stream. How does it look like in the code? You start with a low-level HTTP4S stream. You then have to lift it to yet another abstraction HTTP WebSocket frame. You then decode it to business logic. You run the business logic, and then you have to encode it back. And there are two lines that caught our interest: this merge halt autopongs and merge halt autopings. This comes from this Tapir configuration for auto-pinging on WebSockets. So we took a look at the performance of those, and for that we switched to FS2. And the results were quite interesting. The merge operation turned out to be pretty slow, despite the fact that we are using a more, on paper, arguably more complex par-join unbounded combinator, which combines a stream of streams. It turned out to be faster. So in our case, we don't have a dynamic stream of streams. We just need to merge a fixed number of those streams. So since it was faster than merge, we took a look at the code in the FS2 library. This is the whole code of par-join unbounded. It's not relevant how it works. It's just to show you that it is quite complex. It is really quite a complex code. So if we switch it to a static list, that's the whole code. And this is a pull request that has been merged to FS2. This is another flavor of par-join unbounded on the static list. And it performs better, even better than the dynamic one. So what we did in Tapir 1.10, we hand-coded this merging. We replaced those high-level operators with our low-level merging, and these are the results. The new one is way faster. It can actually handle 24.7 users. Still, we are below HTTP4S. And the final round is to observe, actually, why do we have to merge those streams? It turns out that merging streams in FS2 is a very costly operation. Take a look at R1 and 1.4. This came as a huge surprise for me. Merging a stream with an empty stream makes it 200 times slower. 2 minutes, please. So if we just turn off those high-level Tapir configurations like auto pings and shift it to either our business logic or to server configuration, because many servers support it already, we finally arrive at our turbocharged Tapir, where we can where we handle 25K with ease, and we can handle 41,000 users. So the summary is the following. These are the Tapir versions, and the last bar is the benchmark, is the ceiling, is the HTTP4S. So we are almost there. Takeaways, at least for me, running benchmarks is very hard. It's time-consuming. That's okay. But the problem is that there are many pitfalls, and you really have to pay attention to do it right, because if you do it wrong, it will lie and it will draw false conclusions. So once again, please do watch this talk if you do any benchmarks. And the next nice outcome of that is if you engage in something like this, it's very rewarding, it feels great, and then actually you can make an impact. Tapir has now a separate module for performance, there are blog posts, switch to async-profiler, things have been merged to FS2, so it really pays off and feels great to do such things. The slides are available already. The benchmark repository with all the benchmarks that you have seen here is also available on the GitHub. Thank you very much.